Hello and welcome to this lecture. In this lecture, we're going to see methods for computing limits of functions and ensuring continuity, determining continuity of the function for different forms. So that's going to be the main topic of this lecture. We've already seen definitions for limits of the function, what it means and all that. We've also seen much before how to compute limits for sequences. So this notion of computing limits for functions will be very similar to this computing limits for sequences. The methods we use are very similar. Okay, so without further ado, let's get started. So the first couple of functions for which we can very easily compute limits is the constant function f of x equals c, right? One constant value for all x. And the other function is this identity function. What is this identity function? F of x equals x. It's like y equals x line, right? The reason is any sequence which converges to any point x naught, if you act upon it with f, if you hit it with f, if you look at f of a1, f of a2 also, for the constant function nothing happens, right? Even after the function, the sequence you get is c comma c comma c comma c, and that definitely converges to c, right? So there's no problem. So any sequence, whatever it may be, if it's converging to x naught, the sequence of functions of those values, right, f of a1, f of a2, etc., that converges to c for sure. So we see very clearly limit as extending to x naught of f of x for this constant function is actually c, which is also equal to f of x naught. Okay, so that's very nice, easy to see here. Something very similar happens here for f of x equals x. You take any sequence a1, a2, so on, that converges to x naught, right? So this is my definition for the limit of a function at x naught, right? If you take any sequence that converges to x naught, when f acts upon it, it should converge to some limit. But notice what happens here. When f, which is the identity function, acts on this sequence, you're going to get the same sequence again, right? a1, a2, so on, converges to x naught. F of a1 is a1, f of a2 is a2. Clearly, the f of a1, f of a2 sequence clearly also converges to the same x naught. So limit as extending to x naught of f of x is equal to x naught, which is the same as f of x naught. Okay. So we see here both these functions, the constant function and the identity function, they both have limits at all points on the real line. Every x naught, any x naught you take, they are going to have a limit. Limit exists, and in fact it is equal to f of x naught. So we can conclude that both these functions are in fact continuous at all the points on the real line, which we know from the graph, right? So these two curves clearly are just continuous straight line, and limit exists everywhere. There's no problem, there's no jump, there's no things going off to infinity. Nothing happens in these two functions, and clearly well enough the analytical theoretical definition that we have for continuity and limits is giving us the exact same answer. Okay, so these are two basic things. So our approach to computing anything or solving any problem in this course is to first solve small versions of it and then use it as ingredients in solving bigger versions. This is what we've been doing over and over again. We'll do the same thing here. We picked up a couple of small functions for which we can easily compute limits and determine continuity, and we're going to make use of it in the next step. Okay, so we go from known to new, and that's basically rules for combining limits of functions. The known case is put out here. Okay, limit as extending to x naught of c equals c, limit as extending to x naught of x equals x naught, right? So these are the two known cases, the constant function and the identity function I've written down here. Okay, so what do we know about combining? So this will sound exactly like combining laws for limits of sequences, and that is not strange because after all, limits of functions is also like a limit of sequence, right? So all the combination rules that apply for limits of sequences will apply for limits for functions as well. So supposing I have two functions f of x and g of x for which the limit as extending to x naught exists, right? Both of them exist. Let's say both are finite. Okay, so when it goes to infinity, we usually have that confusion. So let's drop that. We'll only look at the finite case. Both for f of x and g of x, the limit exists at x naught. Let's say we have that. Then we can do scaling, addition, subtraction. We can scale f of x by a constant c, and then that's the limit of that will be c pulled out and limit going in. So this is like taking limits on both sides, and the limit goes inside the operation. The same thing happens here. The limit will distribute over addition. Limit of extending to x naught f of x plus g of x is limit goes inside, do f of x first, limit on g of x first, and then you can add. Same thing with subtraction. Okay, so these are the rules which we used in the sequence side. The same thing we can use for functions. Okay, so there's nothing wrong with that. The proof is like more or less similar. We've been not proving these things in great detail in this class, but you can sort of intuitively see why it should be true. Same thing with multiplication. So you have f of x times g of x, limit as x tending to x naught. This is just going to be a product. Powers, right? Powers with integer powers, f of x raised to the power k. This again, limit will go in. You can do the limit first and then raise the limit to the power k. And then quotient also, I mean ratios, f of x divided by g of x. Again, the limit can go into the numerator separately, denominator separately, and then you can divide. And of course, here you have to assume that the denominator limit is not 0. Okay, otherwise you'll be dividing by 0. That doesn't make sense. Okay, so all these operations are will hold for limits of functions as well, and that's because they hold for sequences. And anyway, limits of functions are a special case of limits of sequences. So these are the rules. And now let's look at what this means for continuity of functions, right? So we know that this constant function and the identity function are continuous. Now, as we do these operations, we observe that if f and g are continuous at x naught, then all these modified versions, the combined versions, are also continuous at x naught. Okay, so these are very easy to see just by these operations. We can see that c times f of x will be continuous at x naught, because the limit will again exactly go to the same function value, right? If f of limit of x tending to x naught, f of x is f of x naught, then for c times f of x also it will be c times f of x naught, right? So since the limit is going in, all these guys will also be continuous at x naught by just this operation, right? C times f of x plus or minus g of x, f of x times g of x, f of x per k, where k is an integer 1, 2, 3, so on, f of x by g of x if g of x naught is not equal to 0. In all these cases, go full screen. Okay. In all these cases also, these functions are all going to be continuous, and that just comes from this simple computation. Okay, I hope you see this. Like for instance, let me just talk about this alone. Supposing this limit is f of x naught and this limit is g of x naught, and the product limit of the product is f of x naught times g of x naught, right? So you see that. So if these two are continuous, then product is continuous also. Okay. So you see here, from known continuous functions, very small, just constant and identity we have, we can quickly see a lot more functions will be continuous in various points. Okay. So and that also depends on these rules for combining limits of functions. Okay. So let's see if we can put this to use in some examples. The first very important and prominent example are polynomial functions. What are polynomial functions? I am denoting it as p of x. These are functions of this form, right? p0 plus p1x plus p2x squared plus so on till pm x power n. So basically, it is scaled combinations of 1x, x square, so on. Okay. Normally, if it's straight line, we'll only do p0 plus p1x. If it's quadratic, we'll do p0 plus p1x plus p2x squared. General polynomial keeps on increasing that, more and more terms are added, and it goes all the way up to x power m. Okay. So usually when you write a polynomial up to x power m, you assume that pm is not equal to 0. I mean, it could be 0, but then the degree is going to go lower. So if you assume pm is not equal to 0, then the degree is m. So degree basically is the largest term that is there with non-zero coefficients. These things are called coefficients: p0, p1, p2, pm. These are coefficients. X is the variable, and you see it goes like that. Okay, so this is a polynomial. Very, very easily, so you can see, using the combining rules and the known limits for constant function and identity function, limit as x tending to x naught of p of x is clearly p of x naught for all x naught, right? So limit will go in. First of all, there are just summations. So limit will go into the summation. Limit for p naught is just p naught. Limit for p1x is p1 x naught. Limit for p2x squared is actually p2 into x, right? Now you use the product rule along with constant scaling. You get p2 times x naught, which is x naught squared, and you repeatedly use this and you get this. The same thing we did for sequences also, right? If you remember, we took the limit inside using the rules, we just combine them. So we have this very nice result that polynomials have a limit at every point, and that is just p of x naught. So clearly, polynomials are continuous at all points of the real. Okay, so these functions are really nice and smooth functions. So if you have any polynomial of this form and if you plot a curve, what do you expect? You expect a smooth continuous line going off throughout. Okay, so straight lines are smooth, any straight line is smooth, any quadratic is smooth, any cubic function is smooth, any quartic function, degree 5 function, degree 6 function, all of them are again smooth and smooth and smooth. You can draw. So this is continuous. Okay, so that's polynomial. And you see how these rules are, we were able to use it very, very quickly and easily here. Okay, so the next comes rational functions. So rational functions are basically, what is rational? A rational function with it has a numerator which is a polynomial of some degree and a denominator which is again a polynomial of some degree. Okay, so we have a numerator which is a polynomial, denominator which is a polynomial, and the rational function is the ratio of the numerator and denominator. Numerator divided by denominator. For every x, this is the value of f of x. Okay, we assume that the largest degree terms are non-zero coefficient. So numerator degree becomes m, denominator degree becomes m. So this is a generic rational function. Again, using the rules that we have for quotient and all that, as long as q of x naught is not equal to 0. Okay, at every point for which the denominator is not 0, you're going to have limit as extending to x naught f of x be equal to f of x naught. The limit will go in, it will go into the numerator separately, denominator separately, and then you just have polynomial here which will work out, but except the denominator should not go to 0. Okay, so that alone you have to make sure. Okay, so this gives you easy ideas of how to do limits for rational functions, and clearly we can conclude that the rational functions are also going to be continuous at all points where the denominator is non-zero. So if you were to draw the plot of a rational function, it's also going to be continuous, except of course when denominator is 0. If denominator is 0, then something can happen there, it can go off to infinity and all that, but otherwise it's going to be a continuous function. Okay, nice. We've used our rules for combining limits of functions in some very easy ways. Let's see some problems. These problems are from this book called Thomas's Calculus. It's 14th edition. It's a book that one can use extensively for a course like this. It's got lots of problems and practice exercises, and I'll urge you to look at it. Okay, so there's also a comment on continuity of these functions. Okay, find the limit and see if limit is for a particular value, but then I'm also asking for comments on continuity. I'll do that as well. Okay, so let's get started. The first couple of problems are very straightforward. I'm not going to spend too much time doing it. So if you look at this function, this is just a polynomial, right? 4x into 3x plus 4 squared. Is it a polynomial? It doesn't look like a polynomial, but you can simplify it and make it into a polynomial. How do you do that? This is 3x plus 4 whole squared. You know how to simplify that. Use multiplication of polynomials and then multiply by 4x. Eventually, you'll get a polynomial. So when you have to compute limit for a polynomial, you simply substitute x equals half inside this, right? So you will get an answer. Okay, I'm not going to do it explicitly. I'll urge you to do it. So 4 into half is 2, 3 by 2 is 1.5, 5.5 whole squared times 2. That's the answer here. Okay, all right. Hopefully you can do this. This is done. Here is another problem, which is again the problem is very simple. It's just a straightforward polynomial and limit as extending to minus 2, which is just plugging in x equals minus 2 and evaluating very carefully, right? So these are easy to do. Same thing with these two problems as well, right? So you see here t equals 2, denominator is non-zero, right? 4 minus 9 is minus 5. So you can simply substitute t equals 2 here and you will get this limit. Likewise here x equal to 3 extending to 3 and denominator is non-zero at 3. So you simply substitute, you will get the answer. Okay, so the first top four problems here are straightforward substitutions. Okay, and since it's working out in such a simple way, I'm not doing it in great detail. There's comments on continuity. This function is continuous everywhere. This function is continuous everywhere on the real line. This function is continuous except when t squared minus 9 is 0. When will t squared minus 9 be 0? When t is plus 3 or minus 3. So this rational function is continuous at all t except for t equals plus or minus 3. Okay, so it's so easy, right? One can very easily do this. What about this x squared plus 7x plus 2? You have to figure out when this denominator will go to 0. Okay, if you do a careful computation, you'll see Is this easy to figure out? Where the roots are, I mean, you have to find out where the roots are, right? So, whether it has roots on the real line or not, you have to figure all that out. Maybe it has, maybe it doesn't have, I don't know. If it has any roots on the real line, it goes off to 0, it won't be continuous there, right? So, how do you figure that out? Minus 7 plus or minus square root of 49 minus 48, okay. Okay, so I think it has roots at minus 3 and minus 4, right, isn't it? So, you can see that denominator, if you put minus 3, you get 9 minus 21 plus 12, that is 0, minus 4, 16 plus 28, minus 28 plus 12, that is also 0. So, minus 4 and minus 3, this thing goes off to 0, okay. So, except for minus 3 and minus 4, this function will be continuous everywhere else, okay. So, see how easy it is. These are very simple things to do, okay. Let us come to the other set of problems here, which seem to be slightly more tricky here. The reason it is tricky is, notice what happens here. So, it is asking you for limit as extending to 5, x minus 5 by x squared minus 25. So, if you just blindly substitute x equals 5 here, you run into a problem. What is the problem you run into? You get a 0 by 0 situation, isn't it? You get a 0 by 0 situation. So, when you get a 0 by 0 situation, you have to be slightly careful, okay. So, here is a very simple rule I will teach you about polynomials. This is called, so supposing you have a polynomial p of x. Suppose p of x naught equals 0, then p of x can be written as x minus x naught times another polynomial, which I will call q of x. Okay, so this is an important result. How do you find out this q of x? You can do a long division. You can put p of x inside and then divide by x minus x naught. You can divide, and then what you have here, finally the remainder will be 0. Okay, so that is what this means, and then what you have here will be q of x. Okay, I hope you remember long division with the polynomials. Quite often this division might be very trivial. You may know some other algebraic identity which will directly tell you this, but this is the basic principle. If you find that for any polynomial, it goes to 0 somewhere, p of x naught, some value x naught for which it goes to 0, then it turns out this x minus x naught is a factor of the polynomial. P of x is x minus x naught times q of x. This, when you divide the polynomial with x minus x naught, after you finish all the division, you should get 0 on the remainder. Okay, and what you left here with will be the quotient. So, x minus x naught times that will give you p of x. So, this is one of the basic principles of polynomials. A lot of identities are based on this calculation. Like for instance, you may know about this very famous identity, right? X squared minus I don't know, a squared is x minus a times x plus a. Okay, it's very easy to verify this. I'll just show you why it's sort of true from this polynomial behavior. So, if you put this as p of x, here's an example. You put this as p of x, you see that p of a is 0. Okay, so you can divide x squared minus a squared, okay, by x minus a. Okay, initial thing has to be x squared, so you'll get x squared minus ax. If you do the subtraction, I'm going to get ax minus x squared, and this will be minus plus a. So, you get ax minus a squared, you get 0. So, this is the quotient, and so you see this thing works out, right. So, tick mark, right. So, you see this is the basic identity. You can do it in so many other ways, but this is the basic way to derive. So, this result is extremely important for polynomials to know. Okay, all right. So, that's good. Armed with this, let's look at this problem. What has happened here? X squared minus 25, it ends up being 0. So, let's look at this. X minus 5 by x squared minus 25, limit as x tending to 5. You're getting this issue of 0 by 0. But notice here, once my denominator goes to 0, I know x minus 5 is there, right? So, it's the same as x minus 5 times x plus 5. Okay, and I can cancel x minus 5 and x minus 5 here because I have only x tending to 5, I do not have x equal to 5. Okay. When I compute limit, I never make x to be equal to 5, I will only tend x to 5. The limit may actually end up becoming the function when 5 is substituted, that is different. But in the limit, I never substitute something equal to 5, right? I only go a sequence which is tending to x naught, not equal to x naught. That is a very crucial, important idea. So, my x minus 5 will not be 0. This is not 0. So, I can cancel these two guys. I get 1 by x plus 5. So, once I cancel, my denominator does not become 0 anymore. So, the limit simply becomes, so my limit simply becomes limit of x tending to 5, 1 by x plus 5 is 1 by 10. See how easy it is. So, instead of doing the limit on this form is somebody has sort of cheated you. Instead of giving 1 by x plus 5, they multiplied numerator and denominator by x minus 5 just to confuse you, and they gave you x minus 5 by x square minus 25. But this form, I mean, it is a slightly different from 1 by x plus 5, but in the limit you just get 1 by 10 because x minus 5 will cancel, which are not becoming equal to 5. Okay. So, this kind of a same sort of principle is used over and over again in all these problems. Okay. In each of these problems, you will face a similar situation. Let's take up this guy now. T tending to minus 1, t squared plus 3t plus 2. If you put t equals minus 1, numerator goes to 0. Okay, you can check that 1 minus 3 plus 2 is 0. Denominator hopefully also goes to 0. Yes, 1 minus of minus 1 plus 1, 2 minus 2, 0. So, you get 0 by 0. When you have a 0 by 0 form, you have to use your division method and cancel out t equals minus 1. So, let me just do this one alone very quickly. T squared plus 3t plus 2 divided by t squared minus t minus 2, it will factor as t plus 1 into t plus 2, this will factor as t plus 1 into t minus 2. You may want to check that because when you put minus 1, both of these guys became 0. So, you have to do that long division. So, how do you do the long division? You do the long division t squared plus 3t plus 2 by t plus 1, and then you will get something. What am I going to get? I am going to get t plus 2 here, and I am not doing it in great detail. I will let you figure it out. This will be t minus 2 and you will get finally 0 here. Okay. So, it is easy to do this, check it out and get some practice with this kind of a thing. So, now you can cancel t plus 1 and t plus 1, you get t plus 2 by t minus 2. So, limit as t tending to minus 1, t plus 2 by t minus 2. It's just if you put minus 1 now here, you get 1 by minus 3. So, it's minus 1 by 3. So, you see how quickly we did this. So, this trick is to just cancel out the offending term, the linear term, t plus 1, which was there in both the numerator and denominator. I gave you a 0 by 0 form. So, because of that, this is not working out. So, we can get rid of that. Okay. I hope that's all right. So, let us come to this this problem. This one is also very easy. I am going to skip this. I will let you do this. So, it seems to have all sorts of problems here, 0 by 0. But then if you manipulate the numerator, you see that you get 2x by x squared minus 1 times x, and the x cancels. So, it is just 2 by x squared minus 1. So, answer ends up being minus 2. Okay. So, you see that you can cancel the x here quite easily. Let us come to this one. Oops, what did I do here? So, let us come to this one, u power 4 minus 81, u power 3 minus 27. If you put u equals 3, again you get a 0 by 0. So, I should be able to factor out a u minus 3. So, this may be, some of you may not be that familiar with this kind of manipulation. So, the u power 4 minus 81 by u power 3 minus 27. So, when I put u equals 3, this u power 3 minus 27 is becoming 0, right. So, let us try this wonderful division. Some of you may know this, this kind of a formula also. So, you will have a u squared here, u power 3 minus 3u squared. So, 3u squared minus 27. So, this is going to be plus 3u squared minus 9u minus 27 plus 9. So, that is 9u minus 27 and you get 0. So, you see here the denominator is simply u minus 3 times u squared plus 3u plus 9. So, for the numerator also you can do the same thing, you will get something like this. So, should I give you the formula or should I do the long division? One of the two is fine. So, you will get u power 4 minus 81 is u minus 3 times u power 3 plus 3 times u squared plus 9 times u plus 27. Ooh, how did I get that? So you can repeat the same division using this u minus 3 and you will get it. So, again this will go as u power 3 plus 3u squared plus 9u plus 27. I hope I got that right. Okay, you can check that. So, then u minus 3 will cancel. So, main point is u minus 3 will cancel and then you can substitute u equals 3 here, right. So, happily you can substitute and you will get what you want. Is that right? Is this right? Check this. If it's not right, you can post a question on the forum. You can correct this also. Okay, good. So, that's nice. So, that's the end of this problem. So, there are many other problems of this kind that one can come up with where you have to do some factoring to figure it out. But the most important fact, very useful fact for your life, I think, is the fact that the polynomials, if you find a 0 of the polynomial, you've also found a factor of the polynomial by division. Okay, that's the end of this lecture. Let's carry on with the next lecture next time. Thank you. Bye bye.